Hello, everybody. I hope you guys are all doing well. Today we are going to be talking about multiplying and dividing radicals. So we'll start with multiplication. And in general, the rule is that when you multiply two radicals with the same index, you essentially multiply the two radicands together. Okay, so something like this, m times k root the kth root of a, I'm not sure how you would say that, times n with the index of k root b is equal to m times n with index k root a times b. Now, an example as to why this works is, let's say you compare the square root of 4 times the square root of 9. Okay, now we know that 4 times 9 is 36. So this should equal the square root of 36. Okay, now if we make sure that this is correct, square root of 4 is 2, and the square root of 9 is 3, and the square root of 36 is 6. So this in fact is true, right? Because 2 times 3 is 6. So these guys, in fact, are equal to one another. And then, of course, if you have almost like a coefficient in front of the radical, then you would just multiply those together as well. Okay, so this is the general rule, and this is why it all works out. Okay, all right, so we're going to practice doing this. Now, what we're going to find, though, is that after we multiply radicals together, they can often be simplified. So we're going to have to do that as well. Okay, so here's an example. 5 square root 3 times the square root of 6. So the number outside is just 5 because the number outside of the square root of 6 is just 1. And then the square root of 3 times the square root of 6, 3 times 6 is 18. So that would be the square root of 18. Okay, now 18 actually has a perfect square factor. Okay, if you prime factorized 18, then you can divide it by 2, and you get 9, and then it's 3 times 3. So we've got this pair of primes in there, right? The pair of primes is 3. So we could pull one of those outside, and what's going to be left inside the radical is a 2. So this is going to be 5 times, we'll pull one of those 3's out, and then we're left with the 2 outside. And so 5 times 3 is 15 times the square root of 2. Okay, so that would be the simplified radical once you multiply these together. Okay, now sometimes we also have this situation where we're almost like multiplying a radical by like a binomial sort of thing. It's the same sort of idea in terms of the distribution, right? We're distributing the multiplication of this radical to both of these radicals. Okay, so for the first one, we're going to get negative 2 times 4 is negative 8. And then square root of 2 times 11 is 22. And c times c cubed is c to the 4. Okay, and then for the second one, negative 2 times negative 3 is positive 6. And we're left with the square root of 11 times 3 is 33. And then we just have a c. Okay, so when we do that, let's see if there's anything that we can simplify. Now, we've got this negative 8 on the outside. If we look at the first radical, and we kind of expand that out, the 22 is 2 times 11, and those are both prime. If we look at the c to the 4, though, and perhaps what I'll do is I'll expand this out all in one line, like we did on Friday. What we're going to get is negative 8 times the square root of 2 times 11 times 4 c's. 1, 2, 3, 4. Okay, plus 6 times 33 is 3 times 11. So 3 times 11 times c. Okay, that's an 11. There we go. Now, there's nothing that we can do with the second one because there's no pair of primes or pair of variables that we can pull out there. But with the first one, there's a couple of pairs here, right? There's a pair of c's and then there's another pair of c's. So I can pull one of them out here, and then another one out. And I'm going to be left with negative 8c times c times the square root of, now 2 times 11 is 22, plus 6 times the square root of 33c. Okay, and all together, that's negative 8c squared, square root 22, plus 6 square root 33c. Okay, so after I multiply out what I started with, this is what I end up with fully simplified. Okay, and then finally, here we're multiplying, this is almost set up as if we were multiplying two binomials together, right? So this is the same sort of idea. I have to start out with the first radical and multiply that by both radicals in the second bracket. So I'm going to do this distribution, distribute the multiplication of the 4 root 2 into both of these radicals, okay? And I'm going to end up with the first one, 4 times the square root of 2 times 7 is 14, okay? And then with the second one, I'm going to have 4 times 5 is 20, and this is subtraction. So minus 20, and then 2 times 14 is 28, so the square root of 28. And then I can move on to the second set of distribution of multiplication, and now I need to multiply the 3 by both radicals in the second bracket. So 3 times the square root of 7, so plus 3 root 7. And then minus 3 times 5 is minus 15, square root of 14. Okay, and I have to see if some of these can simplify. So some of this you can do in your head, right? So you know that 7 is prime, so there's nothing you can do there. If you know 14 is 2 times 7, right? There's no primes there. Or sorry, I'm not saying prime. There's no pairs of primes there. So there's nothing that you can pull out there. The square root of 14 is fully simplified. The 28, though, there might be something that we can do there. So let's see. 28, that's 2 times 14. And the 14 also has a factor of 2. So there is a pair there. There's a pair of 2's. And so I can pull one of those out. Okay. Now what I'm going to end up with is 4 square root of 14 minus 20. And then I can pull one of the 2's out. So times 2. And what's left is this 7 square root of 7 plus 3 square root of 7 minus 15 square root of 14. Okay, and now you can add and subtract some of these radicals together, because if you remember from Friday, any radicals that have the same index and the same radicand can be combined. Okay, so it looks like these guys have the same index and the same radicand, and these guys are going to have the same index and the same radicand. Okay, so maybe I should simplify the second term first. We're going to have 4 square root of 14, and then this is going to be minus 40 square root of 7 plus 3 square root of 7, and then minus 15 square root of 14. Okay, so all together, if I count up how many square roots of 14 do I have 4 minus 15 of them. That's all together negative 11 square root of 14. And then how many square roots of 7 do I have? I have negative 40, and then I add 3, so negative 37 square root of 7. Okay, so simplifying this square root of 28 is very important, because once you do that, you can combine these two terms, this one and this one. Okay. All right, so that's a little bit on multiplication. Now we're going to talk about division. And when we talk about division, we're actually going to incorporate some of the stuff that we talked about with multiplication as well. All right, now dividing radicals. So similar sort of idea with division as to multiplication. If there's numbers on the outside, you would just divide those two. And as long as they have the exact same index, you can also just divide the radicands, okay? Now, again, why does this work? Let's say I have something like the square root of 36 divided by the square root of 4, okay? Well, 36 divided by 4 is 9. So let's compare that to the square root of 9. Well, we know the square root of 9 is 3. Square root of 36 is 6, and the square root of 4 is 2. And this is also equal to 3. So you can see that, yes, you can, in fact, write the square root of 36 over 4. That should equal the square root of 36 over 4, which is the square root of 9. And we can see, yep, those are equal, in fact. Okay? So this is why this works out. Okay? This is why this is true. Now, we can use this property to do something called rationalizing the denominator. And what this is all about is what I like to call sort of good math grammar. When you are sort of leaving a final answer, it is not considered good math etiquette to leave a denominator as an irrational number. Okay, you want to try and avoid that as you can. Now, it's not mathematically incorrect because you'll have the correct value, but it's not considered good math grammar. It's kind of like handing in a formal English essay that has a bunch of emojis all over it. Okay, you don't want to do that. Okay, so here's how we can get around that. We can use this property and what we know about multiplication to rationalize a denominator, okay? Now, if you have a monomial denominator, let's say you have 1 over m root a, then you know, for example, what do I need to multiply the square root of a by to get a rational number? I need to multiply it by itself because the square root of a times the square root of a is just a. Now, the only way for me to do that, so that I can keep the value of this expression, is if I actually multiply it by the square root of a over the square root of a. Because then what I'm doing is I'm just multiplying the expression by 1. So what this is going to end up simplifying to is in the numerator, I'm going to get the square root of a over m times the square root of a times the square root of a is just a, right? Because if you think about it, the square root of a times the square root of a is the square root of a squared. Well, the square root of a squared is just a. Okay, now this may seem to you guys to be a little bit abstract. So what I'd like to do is show you an example with numbers. Let's say you have 1 over root 2. Okay, you want to rationalize that. What you would do is multiply this by the square root of 2 over the square root of 2. Okay, and then what you're going to end up with is the square root of 2 times the square root of 2 is 2. And in the numerator, you're going to have 1 times the square root of 2, which is the square root of 2. Okay, and now what you have is an equivalent number where you have a rational denominator. Okay, the denominator is a rational value, not an irrational value. Okay, so that's the process of rationalizing a denominator. Okay, now, when you have a denominator that is not a monomial, let's say you have a binomial, okay, then what we can do is we can multiply the numerator and denominator by something called the conjugate, okay? And the conjugate relies on difference of squares. So what I want to remind you of is this. Okay, a plus b times a minus b equals a squared minus b squared. Okay, so we know that. We've been doing that for quite a while, since the beginning of 10C. Okay, now if this is true, then this should also be true. Square root of a plus the square root of b times the square root of a minus the square root of b should equal a minus b. Okay, and essentially the reason why is if you, let's say you start with this, with these a squared minus b squared. Well, how do you factor that? Okay, the first term in each bracket is the square root of the first perfect square, right? So if we have a squared, the square root of that is a and a. If you don't have a perfect square, the square root of a is just the square root of a. It's the square root of a. The square root of b is the square root of b and the square root of b. And then you have a plus and a minus. Now, what you get, though, is when you multiply it out, you just have a minus b. You don't have anything irrational in there. And so we can rely on this conjugate principle. These are called conjugates of each other to be able to rationalize the denominator. Okay, and we'll actually practice multiplying this out so that you guys can see what this looks like. Okay, so the conjugate of the square root of a minus the square root of b would be the square root of a plus the square root of b. And you want to multiply that by that over itself. Okay, now when you multiply this out, in the numerator, you're just going to have the square root of a plus the square root of b, because you're just multiplying that by itself. In the denominator, if you expand that out, well, square root of a times the square root of a is just a. And then the next term is going to be the square root of a times the square root of b. That is the square root of a times b. Okay. Now we've distributed this multiplication of the square root of a. Now we got to move on to the multiplication of this term, right? So the first thing that we'll have is minus the square root of b times the square root of a. Well, that is minus root ab. And then finally, we're going to have, so that's this guy. And then finally, we're going to have negative square root b times the square root of b. Well, that's just minus b. Okay, and what happens is, just like in a difference of squares, these two middle terms cancel each other out because it's the same term but opposite signs, right? So these kind of equal 0. And what you're left with is the square root of a plus the square root of b over a minus b. Okay, so that's how the conjugate works. Now I just want to go over some examples of conjugates. Okay, so let's say you have something like root 2 plus 5. Okay, the conjugate of this would be root 2 minus 5. Those are conjugates of one another. Okay, so essentially you have the same terms, but you just have the opposite sign in between them. Okay, you don't put a negative sign in front of both terms. You have to have one of them is a positive in between the two terms, and one of them is a negative in between the two terms. Okay, let's say one of them is 3 root 7 minus 4 root 5. Okay, the other one would be 3 root 7 plus 4 root 5. So that's essentially how the conjugate works. Okay. All right, so let's practice some of this. Okay, So simplify each quotient, identify the values of the variable for which the expression is a real number. So that'll come on the next page. We don't have any variables yet. Okay, so simplify each quotient. Well, first we need to rationalize these quotients. Okay, so we're going to do that first. Now, in order to rationalize these quotients, in the first case, we need to multiply by root 5 over root 5. Okay, now when we do so, what we're going to get is, in the numerator, 5 times the square root of 3 times the square root of 15 is the square root of, the square root of 3 times the square root of 5 is the square root of 15 over 2 times the square root of 5 times the square root of 5 is just 5. Okay, now these 5's cancel. So what we end up with is the square root of 15 over 2. Now you should always check to see, once you multiply two radicals together, to see if this square root of 15 can cancel, or not cancel rather, can simplify. Okay, now if you can do this in your head and you know 15 is 3 times 5 and there's no pair of primes there, then you're good. You don't need to show that work. Okay, all right, let's try the next one. Okay, now this next one, you may think that the easiest way to go about this is to multiply by the square root of 8 over the square root of 8. And I'm going to start with that because my gut tells me that that's what most of you will do. Okay, but afterwards I'm going to show you an even simpler process. Okay, so let's start with multiplying by the square root of 8 over the square root of 8, because I think that that's what you guys will do. Okay, now what you're going to get is 6 times 8 is 48. So the square root of 48 over 8. Okay, now what we need to do though is, there we go. We need to see if there's any perfect square factors in 48, or if there's any pairs of primes. So I'm going to start with 48 and I'm going to prime factorize that. Okay, so it's 2 times 24, and 24 is 2 times 12, and 12 is 2 times 6, and 6 is 2 times 3. And there's a bunch of pairs. There's a 1 pair of 2 and 2 pairs of 2. So I can actually bring out 1 2 and a second 2, and then I'm left with a root 3 over 8. Okay, now that's essentially 4. I don't know why it keeps doing that. Sorry about that, guys. 4 root 3 over 8. And then this can cancel. 4 over 8 is 1 over 2. So this becomes the square root of 3 over 2. Okay, now another way that you can do this is you can do this. If you know that within the radicands, there's already a factor that's common to both. Okay, so I'm actually going to do this part down here because I have some space underneath this problem. Right? And you're like, hey, 6 and 8 already have a common factor, and that common factor is 2. Well, you can break these radicands up, right? The square root of 6 is equal to the square root of 2 times the square root of 3. And the square root of 8 is equal to the square root of 2 times the square root of 4. And now these square root of 2's cancel. And so this is equal to the square root of 3 over the square root of 4. Well, the square root of 4 is just 2. And so you end up with the same answer. Okay, so you can do it that way as well. All right, let's look at some more. Okay, now over here, what I would recommend that you do is if you notice the 6 over 27 actually simplifies first, there's a common factor of 3 in there. Okay, so I would simplify that first. Divide both of those by 3, and you're going to get 3 over 2 times the square root of 6 divided by 3 is 2 over 27 divided by 3 is 9b. Okay, now this 9, remember 9 is a perfect square. So I can actually pull that out right away. 9 is 3 times 3. Now what you need to remember though is that this is in the denominator. So when I pull it out, that factor of 3 has to go into the denominator. Right? It's almost going to be 1/3 that gets pulled out. And then I'm left with 2 over b. Okay, now this 2 over b, I can split this up into, oh, and by the way, look at that. These cancel. Isn't that nice? These factors of 3 cancel. Oh, that's great. Okay, sweet. This 2 over b, I can break that down. Now I have a 1/2 on the outside into 2 radicals. A root 2 rather, over a root b. Okay, and now what I can do is I can rationalize this denominator. So I can multiply this by the square root of b over the square root of b. Okay, and what I'm going to end up with is, in the numerator, well, the square root of 2 times the square root of b is the square root of 2b over 2 times square root of b times the square root of b is just b. Okay, so that would be the simplified answer. Now, we were also asked to state the restrictions on the variable here. Okay, now if you think about the fact that when you're dealing with square roots, you can only have positive radicands, and I have a factor of b inside the radical. Well, b then has to be greater than or equal to 0. Right? Because if it's less than or equal to 0, then the radicand will be negative, and I can't take a negative square root, right? Or I can't take the square root of a negative number, I should put it that way. Okay, so that would be the fully sort of simplified radical. Okay, let's look at this guy. Okay, now this one's kind of tricky because we're dealing with cube roots, and we need to rationalize this. Okay, now with this one, remember you're kind of asking yourself, what do I need to multiply by itself 3 times to get 9p? Now, if this was a square root, we would just multiply it by the square root of 9p, and we'd have 2 of them, and that would equal 9p. Right? Now here, we actually need 3 of these. 3 of these multiplied together. 3 cube root 9p's multiplied together to get 9p. Right now we only have 1 of them. So to get 9p, we need to multiply 2 more cube root 9p's together to get 9p, right? It's kind of like, if you think of even just I don't know why, sorry. Let me fix that a little bit. I think I went too close, so the resolution gets a little bit messed up. Okay, let's see if that helps. If you think of the cube root of 2, I think also, sorry, I'm just going to see if I can fix this a little bit. Ah, that's better. I think I had my pen too thick. Okay, let's try this. If you think of the cube root of 2, okay, if I just multiply that by the cube root of 2 again, that's not going to equal 2 yet. I need to multiply by the cube root of 2 one more time to get 2, right? So it's like right now I have 1 of these. I need 2 more to be able to rationalize it. So what I need to do to rationalize this thing is to multiply it by itself 2 more times. Now, I could also think of that as the cube root of 2 times this guy squared, right? That's the same thing. So that's what I'm going to do here. And that should do the trick. Okay, now I have 1, 2, 3 of these guys, and all together, when I multiply all 3 of them together, I'm going to end up with 9p. Okay, so let's see what that gets us. That's going to give us in the numerator -7 times the cube root of 9p squared over 2 times 9p. Okay, and all together, that will give me -7 cube root 9p squared over 18p. Okay, now here, we're not going to have any restrictions on p because you can take the cube root of a negative number. So in this case, p can be anything, right? If I wanted the cube root of -27, it would be -3 because -3 multiplied by itself 3 times is -27, okay? So with cube roots, you won't have restrictions, but with square roots, you will. Okay? All right, let's try a couple more and then we'll be done. All right, so here's one where we have to just basically rationalize our denominator. So the way to deal with that is to multiply by the conjugate. And in this case, the conjugate is 3 root 5 plus 4. Okay, so what I would recommend is initially start actually multiplying these out fully so that you get a feel for what's happening. And then after a while, you may be able to take some shortcuts. And in fact, we can talk about the shortcuts after we go through the whole process. Okay, okay, so let's see what happens. In the numerator, what we're going to get is 2 times 3 root 5 is 6 root 5. And then 2 times 4 is 8. So plus 8 over, in the denominator, this is going to be 3 times 3 is 9. And root 5 times root 5 is 5. Okay. And then we're going to get 3 root 5 times 4 is 12 root 5. Okay, and then we're going to get -4 times 3 root 5 is minus 12 root 5. And then we're going to get -4 times positive 4 is minus 16. Okay, so these cancel each other out. And that will give us 6 root 5 plus 8 over 9 times 5 is 45. Minus 16, and so all together that's 6 root 5 plus 8 over 29. Okay, so that's that one. Here's another one. Okay, so here again, multiply by the conjugate. In this case, the conjugate of the denominator is 3 root 2 plus 2 root 3 over 3 root 2 plus 2 root 3. Okay, and so in the numerator, when we distribute here, we're going to get root 5 times 3 root 2 is 3 root 10 plus root 5 times 2 root 3 is 2 root 15. And then in the denominator, here, well, 3 times 3 is 9. And root 2 times root 2 is 2. Okay, and then next we go to here. So 3 times 2 is 6. Root 2 times root 3 is root 6. Okay, and then we're going to go to here. And we go negative 2 times 3 is minus 6. Root 3 times root 2 is 6. And then finally we go to here. Negative 2 times 2 is 4. And root 3 times root 3 is 9. Okay, and again, these middle terms cancel. So what we end up with is in the numerator 3 root 10 plus 2 root 15. And in the denominator, we have 18 minus 36. So all together, that's going to be 3 root 10 plus 2 root 15 over negative 18. You know what? I made a mistake. I made a mistake because I hope you guys caught it. My mistake was right here. I'm going to do it in red. Okay, my mistake was here because when I expanded this, I'm glad I made it because this is a really common student mistake too. So I'm human. I make mistakes. Okay, so when I expanded here, I made a mistake. I just caught it now. Okay, here's my mistake. Negative 2 times 2 is 4. That was correct. But root 3 times root 3 is not 9. It's the square root of 9, which is 3. So this should be negative 4 times 3. This should be 12. And this should be 6. Okay, apologies. I hope you guys can follow along with that mistake. But you can see it's an easy trap to fall into. Okay, sorry about that. I demonstrated what not to do. All right, last one. Last one. Okay, 6 over the square root of 4x plus 1. Okay, I'll switch back to black here. Hopefully I won't make another mistake. So we have to multiply by the conjugate. Okay, and the conjugate of the denominator here is the square root of 4x minus 1 over the square root of 4x minus 1. Okay, so in the numerator, 6 times the square root of 4x is just 6 times the square root of 4x. And 6 times negative 1 is minus 6. Okay, over... okay, so the square root of 4x times the square root of 4x. That times that. Square root of 4x times the square root of 4x is just 4x. Okay, and then we're going to have square root of 4x times minus 1 is minus the square root of 4x. And then we're going to get 1 times the square root of 4x, so plus the square root of 4x. And then 1 times negative 1 is minus 1. Okay, so we end up with these canceling. We got 6 times the square root of 4x minus 6 over 4x minus 1. Okay, we're almost done. You might think we're done, but in the first radical in the numerator, we actually have a perfect square in there because 4x is 2 times 2 times x. So this radicand has a pair of primes in it. So we can actually simplify that a little bit. Okay, so I don't have room down below, but I'll do it over here. We can pull a 2 out. So that's going to be 6 times 2 square root x minus 6 over 4x minus 1, which is 12 root x minus 6 over 4x minus 1. Okay, now this guy has a variable in the radicand, and we were asked to state restrictions, and this is a square root. So anytime you have a square root, you have to think about the fact that you cannot take the square root of a negative number. So in this case, x must be greater than or equal to 0. Okay, so I am going to leave it there for today. I will see you guys.